What if a comet from another star system is completely shattering everything we know about cosmic objects? 3IATLAS, an interstellar visitor that has already baffled scientists, is now doing the impossible as it nears Mars. With new data coming in, this comet is showing unpredictable behavior surging in brightness, releasing chemicals we've never seen before, and flaring in ways that challenge the laws of physics. As it races towards Mars, 3IATLAS is revealing secrets from another galaxy, and these secrets could change everything we know about comets, planets, and the universe itself. Is it a natural phenomenon, or is there something far stranger at play? Get ready to dive into the mystery of the century. The closer 3IATLAS gets to Mars, the more alien it looks. Chapter 1: Discovery and Initial Observations. It's easy to imagine that the universe is a silent, predictable place. The stars twinkle, planets orbit in calm harmony, and comets, those beautiful celestial visitors, follow their carefully mapped out paths, dancing around the sun in a rhythm that has been observed for centuries. But every so often, the universe throws us a curveball. On the 26th of July 2025, a faint streak of light appeared in the sky, just another unremarkable dot on a routine sky survey. But this was no ordinary object. As astronomers at the Asteroid Terrestrial Impact Last Alert System, ATLAS, in Chile processed the data, they realized something extraordinary. This wasn't just another comet in our solar system. It was an interstellar visitor, an object traveling through space from another star system, making its first and only pass through our sun's gravitational reach. This was 3IATLAS, a comet from beyond our solar system, a cosmic stranger. Its trajectory was unlike anything we had ever seen, and its speed was staggering. It was moving too fast to be captured by the sun's gravity, and the only reason it was passing through our solar system was by sheer cosmic chance. At first, the data seemed almost routine, a faint, distant object, not yet bright enough to reveal its true nature. The initial estimates suggested that 3IATLAS would remain a faint speck, barely visible to even the most powerful telescopes. But astronomers soon began to notice something peculiar. The comet was brightening far faster than anticipated. Within days, its glow became unusually intense, catching the attention of scientists around the world. This wasn't just a comet from another system, it was behaving differently from any comet observed in our own solar system. Something was off. 3IATLAS wasn't following the expected patterns, and as more data poured in, the inconsistencies started to mount. What could explain its sudden increase in brightness? In typical comets, brightness increases as they approach the sun, with solar radiation causing the nucleus to heat up and release gas and dust. But 3IATLAS was still many millions of kilometers away from the sun, and yet it was already flaring in ways that scientists couldn't explain. The initial surge in brightness seemed to defy the normal laws of cometary physics. 3IATLAS was no ordinary comet. The data started to suggest something far more alien. This wasn't just another icy rock, this was a visitor from the stars, and it was showing us a side of comets we had never seen before. Scientists immediately turned their attention to the composition of 3IATLAS. Comets are often described as the dirty snowballs of the solar system, made of ice, dust, and organic molecules frozen in time since the birth of the planets. As comets approach the sun, they release gases from their frozen interiors, creating a glowing coma and sometimes a dramatic tail. But 3IATLAS wasn't following the expected rules. Its chemical makeup wasn't like that of solar system comets. The spectral data gathered from Earth-based telescopes and space observatories revealed an unexpected mixture of molecules. While many comets release carbon monoxide, water vapor, and methane as they warm, 3IATLAS was releasing far more carbon dioxide than expected. Even more surprising, nickel vapor was detected in the coma, something completely unusual for a comet. Scientists were faced with a mystery. Why was 3IATLAS exhibiting this strange behavior? The data was tantalizing, but it only deepened the questions surrounding the comet's true nature. Some astronomers speculated that interstellar dust might have contaminated the comet's surface, altering its chemical composition. Others wondered if the comet had spent so much time in the interstellar medium, the space between the stars, that its composition had been altered by the cosmic radiation it had encountered over eons. It became clear that this comet had traveled across the galaxy, picking up chemical signatures that didn't belong in the solar system. Every measurement added to the mystery, and as more telescopes turned their gaze toward it, the enigma only deepened. As 3IATLAS drew closer to Mars, scientists began preparing for the unprecedented opportunity to observe it in even greater detail. Mars orbiters such as MAVEN, TGO, MRO, and HOPE were ready to capture the comet from a perspective that Earth-based instruments couldn't provide. With Mars orbiting just beyond Earth, its vantage point would allow for more precise measurements of 3IATLAS's coma and jets. For the first time, two worlds, Earth and Mars, would be watching this interstellar traveler at the same time. The idea that a comet from another star system could be so close, and that Mars orbiters would be able to observe it up close, was nothing short of remarkable. It was a reminder that we are not isolated in our solar system, that the galaxy is vast, and comets, asteroids, and other celestial objects can come from the most unexpected places. But with this discovery came responsibility. 3IATLAS was rare, and the chance to study it was a privilege. This comet wasn't just an object to be observed, it was a key that could unlock the secrets of other planetary systems. It was a moment in history, the kind that only comes along once in a lifetime, and scientists everywhere were determined to gather as much data as possible before it passed us by forever. The mystery of 3IATLAS was just beginning. The comet's sudden brightening, its unusual chemical composition, and its interstellar origins were only the beginning of the story. As it neared Mars, new data would emerge, revealing even more about this alien visitor. In the coming months, 3IATLAS would continue to reveal the impossible as it passed through our solar system, and with each passing day, it brought us one step closer to solving the mystery of this rare interstellar traveler. Chapter 2: New Spectroscopic Data, a Glimpse of Alien Chemistry. When 3IATLAS was first detected, it was a mere point of light against the black canvas of space. But as astronomers turned their instruments toward it, they quickly realized they were witnessing something far more extraordinary. This comet, a visitor from another star system, was not following the expected behavior of solar system comets. The first clue that something was amiss came from the spectroscopic data, which began revealing hints of unusual chemistry. Spectroscopy, the science of splitting light into its component wavelengths, is a powerful tool for understanding the composition of distant objects. By analyzing the light emitted or reflected by a comet, astronomers can determine the molecules present in its coma. In typical comets, the spectra are dominated by familiar compounds: water vapor, carbon monoxide, methane, and carbon dioxide. These molecules are what we expect to find in comets that are born in the outer reaches of our solar system, frozen relics from the birth of the planets. However, 3IATLAS presented something different. The first clue came from its green glow, the signature feature of many comets. In solar system comets, the green glow is caused by diatomic carbon, C2, a molecule that fluoresces under the ultraviolet light of the sunday. But as astronomers began to analyze the spectra of 3IATLAS, they found that the typical C2 emissions were almost absent. This was not the first time a comet had exhibited unexpected chemistry, but it was certainly unusual enough to raise eyebrows. What could be causing this green glow if it wasn't C2? Further analysis revealed an even more puzzling discovery. Instead of the typical mixture of carbon-based molecules, 3IATLAS was found to be rich in carbon dioxide, a substance not typically found in high concentrations in comets so far from the sunday. While carbon dioxide is common in the atmospheres of planets like Earth, it's not the usual product of sublimating cometary ices. What was even more unexpected was the presence of cyanogen, CN3, a toxic molecule that forms under specific conditions, usually in the presence of high amounts of carbon compounds. Cyanogen had never been found in such significant quantities in a solar system comet before. This was the first time it had been detected at such high levels in an interstellar comet. The implications of these findings were profound. The presence of cyanogen, coupled with the high levels of carbon dioxide, suggested that 3IATLAS contained chemistry that was radically different from what we typically observe in comets from our own solar system. Could this be the result of the comet's long journey through interstellar space, where it was exposed to different cosmic environments, including radiation, cosmic rays, and the cold, empty void between stars? The most perplexing discovery, however, came from the unexpected presence of nickel vapor. Metals, like nickel, are not easily vaporized in the cold depths of space. Yet 3IATLAS was releasing detectable amounts of nickel into its coma, something that had never been observed in any known comet at this distance from the sunday. In typical solar system comets, metals like nickel are locked in dust grains, not freely vaporized. So, what was different about this comet? Why was it releasing metal vapor at such high concentrations? One possibility was that 3I-ATLAS had formed in a star system with a radically different chemical makeup, where metallic elements like nickel were more abundant or behaved differently than in our solar system. Alternatively, the long journey through interstellar space could have caused some of the comet's metals to become more volatile. Interstellar comets, unlike those born in the solar system, are exposed to different conditions, such as cosmic radiation, which could cause chemical changes that make normally stable compounds more reactive. Could this be what was happening to the nickel in 3I-ATLAS? Scientists were quick to point out that these findings raised more questions than answers. Could the high concentration of carbon dioxide indicate a different type of ice in the nucleus of 3I-ATLAS, one that sublimates more readily when exposed to sunlight? Or could the comet's unusual green glow be the result of an entirely different molecule, something that had yet to be discovered in the spectrum of any known comet? While scientists were careful not to jump to conclusions, the data pointed to the possibility that 3I-ATLAS could be a chemical anomaly, a comet whose formation and journey had shaped it in ways we did not fully understand. Could the environment around its original star have influenced its chemical composition, making it behave differently from solar system comets? Or was this comet a relic from a planetary system whose conditions were so alien that they defied our current models of cometary chemistry? As the comet approached Mars, astronomers hoped that Mars orbiters MAVEN, TGO, MRO, and HOPE would provide even more detailed spectroscopic data that could help answer these questions. The Mars orbiters would be able to capture the comet from a different perspective, revealing new features that were not visible from Earth. Scientists were particularly interested in the comet's jets and gas plumes, which could reveal even more about its internal structure and the processes driving its activity. Mars's vantage point offered a unique opportunity to study 3I-ATLAS from a second planetary perspective. From Earth, we had already observed the comet's asymmetric coma and the faint jets that were ejecting gas and dust. But from Mars, the orbiters would be able to observe these features in much greater detail. Would the comet's activity increase as it got closer to the Sun? Would the green glow intensify, or would it shift in color? These were questions that could only be answered through Mars-based observations, where scientists would be able to track the comet's behavior from a second, distant point in the solar system. In the meantime, Earth-based telescopes continued to monitor the comet's activity, capturing images and spectra that provided a steady stream of data. As 3I-ATLAS approached perihelion, the point in its orbit closest to the Sun, astronomers anticipated that its activity would intensify. But would it flare up again in the same way it had before, or would its behavior continue to defy expectations? The spectroscopic data coming in from Earth-based telescopes, Mars orbiters, and the Hubble Space Telescope was already changing the way we viewed this interstellar traveler. Its unusual chemistry, its unpredictable behavior, and its alien origins were pointing to the possibility that 3I-ATLAS was a cosmic anomaly, one that could reveal new secrets about the processes that govern the formation of planetary systems. As the comet continued on its journey, the data kept rolling in, each observation adding a new layer of mystery. What was it about 3I-ATLAS that made it so different from comets we've studied in the past? Was it the influence of its original star system, or the passage through interstellar space that shaped its chemical makeup? Could the presence of nickel vapor and unusual chemical signatures suggest something more profound, perhaps even pointing to processes that occur in other star systems? The more we learned, the more it became clear. 3I-ATLAS was rewriting the rules, and as it neared Mars, the excitement was palpable. This was a comet that had traveled light years to reach our solar system, and every piece of data brought us one step closer to understanding its alien origins. Chapter 3: Mars Orbiters Take the Lead, a Rare Vantage Point. As 3I-ATLAS continued its journey toward the inner solar system, the excitement in the scientific community grew. The comet, an interstellar wanderer from a distant star system, had already defied expectations with its unusual behavior, its sudden brightening, alien chemistry, and unpredictable outbursts. But the real opportunity for discovery was yet to come. As 3I-ATLAS approached Mars, the Mars orbiters prepared for a unique observational campaign that would provide the most detailed picture yet of this mysterious visitor. Mars, often called the Red Planet, had long been a focus of exploration, its surface mapped and studied in detail by spacecraft like NASA's Mars Reconnaissance Orbiter, MRO, and MAVEN. But in October 2025, the red planet became more than just a target of planetary exploration. It became a vantage point from which to study 3IATLAS up close. The interstellar comet's path brought it remarkably close to Mars, offering a chance to observe it not just from Earth, but from a second planetary perspective. MAVEN, TGO, MRO, and HOPE Mars's orbiting spacecraft were perfectly positioned to capture high-resolution images, measure ultraviolet and infrared emissions, and study the comet's chemical composition in unprecedented detail. The fact that Mars orbiters could observe 3IATLAS at such a close range made this a once-in-a-lifetime opportunity to gather data that would forever change our understanding of interstellar objects. MAVEN, NASA's Mars Atmosphere and Volatile Evolution mission, was initially designed to study the Martian atmosphere and its interaction with the solar wind, but its ultraviolet spectrometer and neutral particle analyzer made it ideal for measuring the gases being released from 3IATLAS's coma. As the comet approached, MAVEN's instruments began to focus on specific emission lines of carbon, hydrogen, and oxygen, allowing scientists to trace the outgassing activity and even track the comet's rotation. The Trace Gas Orbiter, TGO, an ESA mission, was equipped with instruments capable of detecting subtle temperature variations in the comet's coma. This information would reveal thermal gradients and could help scientists understand how the comet's surface interacts with solar radiation. By measuring the changes in the heat emitted from the comet's nucleus, TGO could help pinpoint areas of active sublimation and perhaps even track the comet's internal structure. Meanwhile, MRO, Mars Reconnaissance Orbiter, with its HiRISE camera, provided the highest resolution images of the comet's coma. HiRISE, capable of resolving features just a meter across, was perfectly suited for capturing the comet's fine structure jets of gas and dust, surface irregularities, and subtle variations in the coma's shape. The data captured by HiRISE would be used to create a detailed map of the comet's activity, providing scientists with valuable information about its nucleus and composition. The HOPE probe, launched by the UAE, was also in a prime position to observe 3IATLAS from Mars orbit. HOPE's multispectral imaging system allowed it to capture broad, global images of the comet's interaction with the surrounding solar wind and Mars's thin atmosphere. HOPE's ability to provide a comprehensive, wide-field view of the comet from orbit complemented the more focused observations from the other orbiters, adding important context to the data being collected. This collaboration between Mars orbiters offered a comprehensive, multi-dimensional view of 3IATLAS that Earth-based telescopes simply couldn't provide. While Earth-based observatories had already provided essential data about the comet's early behavior, the view from Mars allowed scientists to study 3IATLAS's jets, coma structure, and gaseous emissions from an entirely new angle. The two planetary perspectives provided an unprecedented level of detail and accuracy, allowing scientists to triangulate measurements and produce a more complete picture of the comet's dynamics. For example, HiRISE could capture high-resolution images of the comet's coma from one direction, while MAVEN could analyze the ultraviolet emissions from gases escaping the comet's surface in another direction. Combining these measurements allowed scientists to track the movement of gas and dust as they were released from the nucleus, enabling them to calculate the mass loss rate and estimate how much material was being ejected into space. Moreover, the alignment of Mars, Earth, and the comet allowed astronomers to take advantage of multiple observation platforms. While Mars orbiters captured detailed imagery and chemical data, Earth-based telescopes continued to monitor the comet's brightness and track its position in the sky. This combination of observational power provided a level of detail never before possible for an interstellar object. The observations made by Mars orbiters were particularly important because 3IATLAS's close approach offered a unique opportunity to study an interstellar comet in real time as it responded to solar heating. The comet had already shown an ability to flare up unpredictably, and scientists were eager to track any further outbursts, chemical changes, or physical alterations to the comet's structure. Mars's orbiters were in an ideal position to do just that. But the value of these observations wasn't limited to 3IATLAS's chemistry and activity. This mission also offered a rare opportunity to study the interstellar medium, the environment between stars. 3IATLAS had traveled through this void for millions, perhaps billions of years, and its composition could reveal crucial information about the materials that exist in the space between stars. By studying this comet's chemical makeup and how it reacts to the sun's radiation, scientists hope to gain insights into the interstellar dust and gases that might influence the formation of stars and planets in other star systems. In addition, 3IATLAS was not alone in its journey. The comet's passage through the solar system and near its perihelion was expected to generate an influx of charged particles and solar wind that could interact with Mars's magnetosphere. Mars, unlike Earth, lacks a strong magnetic field, and any interaction between the solar wind and the comet's tail could provide insights into the dynamics of magnetospheric shielding and the interaction of comets with planetary environments. As the comet passed by Mars, scientists also kept an eye on the comet's trajectory. With its hyperbolic orbit, 3IATLAS was traveling too fast to be captured by the Sun's gravity. Its path would carry it outward, past the outer planets, and into the deep reaches of interstellar space. But its close pass to Mars provided an ideal opportunity to measure its velocity and refine the models of how such objects move through the solar system. The more data collected, the more accurate the predictions for other interstellar objects in the future would become. Perhaps the most compelling aspect of this observation campaign was the sense of collaboration. Scientists around the world from the United States, Europe, the UAE, and beyond came together to study this interstellar comet. Mars orbiters, Earth-based, telescopes, and space-based observatories all contributed to a collective effort that spanned across continents, cultures, and scientific disciplines. The comet's passage was an international mission, where the goal was not just to learn about 3IATLAS, but to understand the broader implications for our place in the universe. Mars orbiters, equipped with the most sophisticated tools ever sent to another planet, played a pivotal role in uncovering the secrets of 3IATLAS. In this way, Mars's orbiters served as our eyes in the sky, capturing data that would continue to shape the way we understand both the solar system and the interstellar medium for years to come. With each observation, scientists moved one step closer to unlocking the mysteries of this comet, shedding light on the alien chemistry and cosmic history that 3IATLAS carries with it from the distant stars. As 3IATLAS continued its journey, the value of these observations grew clearer. The Mars orbiters' contributions were not just valuable for studying this single comet, they were a step forward in our ability to study interstellar objects. With each data point, each image, and each spectrum, we learned more about alien chemistry, the interstellar environment, and the nature of cosmic wanderers that will shape the future of space exploration. Chapter 4. Unexpected outbursts. What's triggering the explosive activity? By the time 3IATLAS had made its way closer to the inner solar system, scientists had already witnessed its erratic behavior. Its sudden brightening and unpredictable outbursts had become one of the most exciting aspects of its journey. These fluctuations in brightness weren't just the usual seasonal dimming or brightening associated with comets. 3IATLAS was showing explosive activity that was far more intense and unpredictable than anything previously seen in typical solar system comets. While astronomers had initially expected the comet to gradually warm and release gas and dust as it neared the Sun, they could never have predicted the scale and suddenness of the eruptions. In early September, the comet experienced a 20 times brightening, an event that sent shockwaves through the astronomical community. This outburst didn't just make the comet brighter, it caused the comet's coma, the cloud of gas and dust surrounding the nucleus, to expand dramatically, with jets of gas shooting from the nucleus in highly localized bursts. The brightening was so intense that 3IATLAS briefly became visible to the naked eye, a strange and sudden intruder in the skies. Scientists were quick to observe and analyze the data, but the eruption defied easy explanation. What could be causing such violent outbursts from a comet far beyond the normal reach of solar radiation? The increasing intensity of these eruptions hinted at an internal mechanism that hadn't been accounted for in previous cometary models. What was triggering these violent eruptions? Was it the sun's heat, internal pressure, or something far more complex? Internal mechanisms, pressure buildup, or structural collapse? One of the primary theories behind the outbursts focused on internal pressure. As 3IATLAS moved closer to the Sun, solar radiation began to heat its surface, causing the volatile compounds buried beneath the icy exterior to sublimate. This process was expected, but what if the interior of the comet was under excessive pressure? Could the sublimation of gases be building up beneath the surface, creating a volcanic-like eruption? For most solar system comets, sublimation is a relatively gradual process. As the Sun heats the nucleus, it releases gas and dust in a steady flow, creating the familiar coma and tail. However, in 3IATLAS, the bursts were far more sudden and intense. This suggested that pockets of gas trapped deep within the comet's nucleus could be pressurized to the point where they were exploding outward. The rapid release of gas could create shockwaves in the coma, causing the comet to flare up dramatically, as seen in the early brightening. Scientists also speculated that the comet's surface structure could be playing a role in the outbursts. Cometary nuclei are often coated with a hard outer crust of ice and dust, but beneath this, there may be pockets of volatile ices that remain shielded until a break or crack appears. The comet's rotational forces could create stress on the surface, causing fractures or fissures that expose fresh layers of volatile material. These fractures could lead to sudden eruptions as trapped gases beneath the surface are released in an explosive burst. In a sense, 3IATLAS could be acting like a cosmic pressure cooker, its surface slowly cracking open under the strain of internal pressure. Solar heating. Unexpected reactions. Another contributing factor to the outbursts could be solar heating, but not in the way scientists had originally predicted. As 3IATLAS neared perihelion, the point in its orbit closest to the Sun, the increase in sunlight was expected to trigger the usual sublimation of water, methane, and carbon monoxide. However, the chemical composition of 3IATLAS was anything but typical. As mentioned in previous chapters, the comet was releasing unusually high levels of carbon dioxide and cyanogen compounds that are typically more stable and less volatile than the substances found in solar system comets. What was unusual here was that these molecules weren't just sublimating gradually, they were reacting in a way that created unpredictable surges of gas. The combination of solar radiation and the presence of alien compounds might be causing chemical reactions on the comet's surface, leading to sudden bursts of activity. Solar ultraviolet radiation could be breaking down carbon dioxide into simpler molecules, releasing gas in a violent, unexpected way. Similarly, the presence of cyanogen, a compound known to be highly reactive, could be contributing to the explosive bursts. This chemical instability could be contributing to the strange outbursts observed on the comet. Could 3IATLAS's alien chemistry be making it react to the Sun in ways that no other comet had? Its unexpected volatility, from green emissions to the release of highly reactive gases, was suggesting that the comet might not just be heating up due to solar radiation. Instead, the very composition of 3IATLAS might be triggering chemical explosions beneath the surface, setting off eruptions that were both sudden and powerful. Rotational dynamics. Could spinning be causing the eruptions? Another hypothesis being explored was that the rotation of 3IATLAS itself could be causing or contributing to the explosive outbursts. As comets spin, their surfaces experience varying amounts of heating from the Sun, with regions facing the Sun heating up much faster than the regions in shadow. The result is that volatile compounds on the sunlit side may sublimate at different rates than those on the dark side of the nucleus, creating thermal stresses. Over time, these stresses could build up in certain regions of the comet's surface. If the spin rate is fast enough, or if there are certain surface features that expose volatile areas to sunlight more frequently, then the thermal expansion and contraction could create cracks or fractures in the surface, releasing gas in a burst. These sudden eruptions could explain the observed flaring and jets of gas from the comet's nucleus. The spin rate of 3IATLAS could be a key factor in the intensity and unpredictability of its outbursts, suggesting that rotation-induced stress could be playing a larger role than previously understood. The role of the solar wind. The solar wind could also be influencing the behavior of 3IATLAS. As the comet approaches the inner solar system, the solar wind, a stream of charged particles emitted by the Sun, begins to interact with the comet's coma and tail. Solar wind particles can ignite chemical reactions on the comet's surface or push gas jets outward, accelerating the release of material. This interaction could cause localized heating, which in turn might trigger further outbursts of gas. In addition, the solar wind can cause the coma's structure to change. As the comet's tail is pushed away from the Sun by solar radiation and solar wind, it can cause the jets of gas to align or become more irregular. The changes in the coma structure could contribute to the comet's burst-like behavior, producing sudden surges of gas and dust that lead to the dramatic brightening observed. Mars orbiter observations, the next step in understanding. As 3IATLAS approaches Mars, the Mars orbiters are in a prime position to capture more detailed data about the comet's behavior. Mars orbiters like MAVEN, TGO, MRO, and HOPE will be able to measure gas jets, temperature changes, and chemical emissions in real time, providing invaluable information about what's happening beneath the surface of the comet. By analyzing the outbursts, scientists can begin to separate the effects of solar radiation, internal pressure, and rotational forces, helping them to build a more complete picture of 3IATLAS's internal dynamics. Mars's orbital position offers a unique vantage point, enabling scientists to track the comet as it interacts with the sun's radiation and the solar wind, giving us a new understanding of how interstellar comets behave as they approach the inner solar system. A cosmic puzzle. As the data continues to pour in, it's clear that 3IATLAS is breaking the rules. From its green glow to its outbursts and unpredictable chemistry, the comet is rewriting our understanding of how comets behave, especially those from beyond our solar system. Every observation, every piece of data, adds to the cosmic puzzle. What's causing these explosive events? Is it the comet's alien chemistry, the internal pressure, or the solar wind's interaction with the comet's surface? As 3IATLAS nears Mars, the answers may finally begin to emerge, giving scientists and the world a glimpse into the unknown processes that govern interstellar bodies. For now, the mystery deepens, and the cosmic event of the century continues. Chapter 5. The Mystery of 3IATLAS's Origin. When a comet like 3IATLAS enters our solar system, it brings with it more than just a trail of gas and dust, it brings an entire cosmic history. The journey of 3IATLAS, which has travelled for eons through the dark reaches of interstellar space, holds secrets not only about its composition, but also about its origin. Where did it come from? What star system did it belong to? And most importantly, what can it teach us about the universe beyond the familiar realms of our solar system? The initial discovery of 3IATLAS was stunning enough. A comet from another star system, a true interstellar object, was a rarity, a phenomenon that few in the scientific community had ever expected to witness. But as astronomers gathered more data on its behavior, chemistry, and trajectory, it became clear that 3IATLAS was much more than just a passing comet. It was a cosmic messenger, offering us a glimpse into the conditions of a star system far beyond our own. To understand the full significance of 3IATLAS's origin, we must first examine how objects like comets form in the broader galaxy. In our own solar system, comets are believed to originate in the Kuiper belt and the Oort cloud, two regions filled with icy bodies. These objects form around stars, gathering dust and gas in the cold outskirts of a planetary system, remaining mostly unchanged for billions of years. As they travel through the inner solar system, the heat from the sun sublimates their icy cores, creating the familiar glowing comas and tails. But 3IATLAS, as an interstellar object, could not have formed in the same way as solar system comets. It did not originate in our solar system. It came from somewhere else, somewhere far beyond the reaches of our sun's gravity. Its hyperbolic trajectory, a path that takes it through the solar system on a one-way journey, indicates that it has been traveling through the interstellar medium for millions, if not billions of years. The comet's trajectory suggests it was ejected from a distant star system, perhaps following the same processes that create comets in our own Oort cloud, but under completely different conditions. Scientists are still piecing together the exact origin of 3IATLAS, but its path through the galaxy offers important clues. Its speed, traveling far faster than most solar system comets, suggests it has been accelerating under the gravitational influence of distant stars. The journey it has made across the void of interstellar space, likely taking millions of years, has left it with a chemical signature that is radically different from comets in our own solar system. In particular, the chemical anomalies observed in 3IATLAS are the most telling signs of its alien origin. The comet's green glow, its unusual chemical makeup, and the presence of compounds like cyanogen and nickel vapor suggest that it formed in an environment that is fundamentally different from the cold, icy outskirts of the solar system. These chemicals, often more reactive and volatile than the substances typically found in solar system comets, suggest that 3IATLAS was exposed to different physical conditions, perhaps at its birth, or throughout its journey through interstellar space. One of the most remarkable things about 3IATLAS is the traceable impact of its interstellar journey. Unlike solar system comets, which are typically shielded from cosmic radiation by the gravitational pull of the sun and the planets, 3IATLAS has been exposed to the harsh conditions of interstellar space. For billions of years, it has been bombarded by cosmic rays, high-energy particles that slowly chip away at its surface and alter its chemistry. As a result, the comet's surface has likely undergone significant alterations, both chemically and structurally, over the course of its long journey. Some scientists believe that the comet's unusual chemistry, including the high levels of carbon dioxide, cyanogen, and nickel vapor, may be the result of radiation-induced reactions. Over its long journey, 3IATLAS could have been exposed to cosmic radiation that caused chemical changes in its icy surface. This radiation could have broken down complex organic molecules, releasing simpler gases like carbon dioxide and cyanogen into the coma. This process could explain the comet's alien chemistry. It was shaped by cosmic radiation, and not by the same forces that govern solar system bodies. In addition to cosmic radiation, 3IATLAS's path through the interstellar medium would have exposed it to interstellar dust particles and gases scattered between the stars. These particles may have become trapped within the comet's surface, contributing to its unusual chemical composition. Some of the volatile gases and metals observed in the comet's coma could have originated in the interstellar medium itself, collected by 3IATLAS as it passed through the vast emptiness between stars. Interestingly, the unusual outbursts of 3IATLAS could be linked to its long journey through interstellar space. As 3IATLAS approaches the Sun, the increasing heat may be releasing gases that have been trapped in the comet for millennia. These gases, formed under the extreme conditions of the interstellar medium, could behave differently from the usual cometary gases, triggering explosive bursts and flares. The comet's volatile nature may be the result of chemical instability caused by radiation and cosmic exposure, not just the typical processes of sublimation. As the comet gets closer to the Sun and reaches its perihelion, scientists are hoping to see even more chemical changes. What new compounds will be revealed? Could there be even more surprises in store? The close approach to Mars is an invaluable opportunity to capture more data about this alien visitor. Mars orbiters like MAVEN, TGO, and HiRISE will be able to study 3IATLAS from a different perspective, helping scientists unravel the comet's origins and uncover more about the alien chemistry that makes it so unique. 3IATLAS offers a rare glimpse into the distant past, a look at the conditions that existed in another star system, long before it became the comet we see today. Its chemical composition may reflect the conditions of its home system, and its long journey through interstellar space may have shaped it in ways we've only just begun to understand. As it nears Mars, 3IATLAS presents a rare and once-in-a-lifetime opportunity to study the chemistry of the cosmos, to observe how objects from other star systems behave, and to learn what happens when interstellar bodies pass through our solar system. But the real question is, what does this mean for us in terms of future exploration? The study of 3IATLAS could help us refine our understanding of planetary formation, cometary dynamics, and even the possibility of life elsewhere in the universe. The comet's alien origins suggest that our galaxy is full of worlds and systems very different from our own. What else is out there, waiting to be discovered? As scientists continue to study the comet, one thing becomes clear. 3IATLAS is rewriting the rules of what we know about comets, planetary systems, and even interstellar space. It's a cosmic anomaly, a fragment of a distant star system that has traveled millions of light years across the galaxy to teach us about the nature of the universe. And in the process, it is deepening our understanding of just how much there is still to discover. Chapter 6. Closer to Mars, the final observations. As 3IATLAS hurtled through the solar system, racing towards its closest approach to Mars, the scientific community stood at the edge of a once-in-a-lifetime opportunity. For months, astronomers had been tracking the comet's every movement, but now the comet was entering the final stretch. The data collected from Earth and Mars orbiters had already revealed that 3IATLAS was no ordinary comet. Its behavior had defied expectations, and its chemical composition was so alien that it seemed to come from another galaxy entirely. But the real revelations were just around the corner. Mars, our neighbor in the solar system, had become the focal point of this cosmic spectacle. As 3IATLAS drew closer, the orbiters surrounding the red planet were perfectly positioned to capture unprecedented data. Mars, once just a target of robotic exploration, now played an essential role in unraveling the mysteries of an interstellar visitor. Mars's orbit allowed the spacecraft to capture the comet from a second vantage point, one that Earth alone could not provide. Mars orbiters in position. By early October 2025, the Mars Reconnaissance Orbiter, MRO, MAVEN, TGO, and the HOPE probe were fully prepared to observe 3IATLAS. These spacecraft had spent years circling the red planet, studying its atmosphere, surface, and weather patterns, but they were now recalibrating their instruments to focus on the comet. The precision of these instruments, high-resolution cameras, spectrometers, and imaging systems meant that they would be able to provide the most detailed data possible on 3IATLAS. This was the closest view ever of an interstellar comet, and the Mars orbiters were poised to collect data that would shape our understanding of comets, chemical processes, and planetary systems for decades to come. MAVEN, for instance, with its ultraviolet spectrometer, was well equipped to study the emissions of gas and dust escaping the comet's nucleus. The carbon dioxide and cyanogen levels observed earlier in the journey were expected to fluctuate as 3IATLAS neared the Sun, so MAVEN's sensitive instruments would track any new emissions, particularly hydrogen and oxygen in the coma. Meanwhile, TGO TRACE gas orbiter, which had been studying the Martian atmosphere for years, was tasked with measuring the thermal radiation from the comet's nucleus. This data would help determine which parts of the nucleus were becoming active as the comet neared its perihelion, the closest point to the sunday. TGO's infrared spectrometers would be able to detect temperature gradients across the surface of 3IATLAS, revealing insights into its structure and internal processes. MRO's high-rise camera, capable of resolving features as small as 1 meter across, had been one of the most powerful tools in observing the Martian surface. Now, its high-resolution capabilities would be directed toward the comet's coma, capturing the intricate details of the gas and dust jets that had become so characteristic of 3IATLAS. These observations would allow scientists to build a detailed three-dimensional model of the comet's surface activity. In addition, the HOPE probe launched by the UAE was strategically positioned to provide broad-field imaging of the comet's interaction with the solar wind. HOPE's imaging instruments, sensitive to a variety of wavelengths, would give scientists the most complete picture of the spatial orientation of the comet relative to Mars and Earth. HOPE was designed to study Mars's weather and atmosphere, but its ability to capture global images from orbit made it an ideal tool for studying 3IATLAS's behavior as it moved through the inner solar system. The power of these orbiters lay in their ability to capture the same object from multiple angles. While Mars orbiters looked from one perspective, Earth-based telescopes were able to monitor the comet from another. By combining the two, scientists had the chance to gain a more accurate and detailed understanding of 3IATLAS's activity and composition than ever before. A glimpse into the comet's core. As 3IATLAS neared Mars, the comet's jets became more pronounced. Outbursts of gas and dust shot from its surface in highly localized bursts, giving it an increasingly irregular appearance. HiRISE on MRO was able to capture the changes in the comet's coma with incredible detail. Images from earlier in the journey had shown a relatively symmetrical cloud of dust and gas surrounding the nucleus, but now the coma appeared asymmetrical, with prominent jets bursting from one side. These jets were powerful, and scientists began to track their direction and velocity, looking for patterns that could give clues to the internal structure of 3IATLAS. The comet's spin rate and the heat it was receiving from the sun would influence where and when these jets were released. Some scientists theorized that the rotation of the nucleus was creating areas of stress and tension that led to bursts of activity on one side of the comet. Others suggested that the chemical composition of the comet's surface was causing certain regions to become more active than others. MAVEN's instruments also picked up ultraviolet emissions from the expanding coma. These emissions were caused by the comet's gases interacting with solar radiation, releasing energy in the form of light. The sudden brightening of the comet that had been observed earlier was likely linked to an increase in outgassing, a process by which the comet released volatile gases into space. As 3IATLAS approached perihelion, scientists expected the outburst to become even more intense, making it an ideal time for the orbiters to capture crucial data. Interstellar chemistry revealed. As 3IATLAS moved closer to Mars, scientists began to focus more on its alien chemistry. Early in its journey, carbon dioxide had been detected in unusually high levels, and cyanogen, a toxic molecule that is rarely seen in comets, had been found in the comet's coma. These chemical signatures were unlike those of typical solar system comets, which are usually rich in carbon monoxide and methane. The presence of cyanogen, a highly reactive molecule, was especially surprising. With Mars orbiters in place to observe the comet from a different perspective, scientists hope to gain further insight into these unusual compounds. The infrared spectra captured by TGO would be crucial in understanding the temperature at which these compounds were sublimating, providing clues to the comet's internal temperature and structure. MAVEN's ultraviolet spectrometer could track gas emissions from the comet in real time, allowing scientists to monitor how the comet's chemical composition changed as it neared the Sunday. The presence of nickel vapor in the coma had been another surprising discovery. Metals like nickel are rarely found in the gas phase in comets, especially at distances so far from the Sunday. This anomaly suggested that 3IATLAS may have formed in a different kind of environment, one where metals behaved differently, or perhaps one where the process of cosmic radiation had caused changes to the comet's surface that wouldn't be seen in typical solar system comets. Looking forward, the final approach. As perihelion drew nearer, 3IATLAS continued to defy expectations. The comet's activity had intensified in recent weeks, and scientists were eager to see if it would produce another dramatic outburst as it reached its closest point to the Sunday. The combination of solar heating, rotational stress, and chemical volatility made it highly probable that 3IATLAS would continue to release bursts of gas and dust, giving scientists a last opportunity to capture data before the comet moved out of the solar system. At Mars, the orbiters were poised for the final observations. As 3IATLAS passed within 28 million kilometers of the red planet, they would provide the most detailed images and spectra of the comet's coma ever recorded. This data, along with observations from Earth, would allow scientists to complete their 3D model of the comet and study its final stages of activity as it prepared to move on. The cosmic journey continues. As 3IATLAS moved past Mars, the comet would continue on its journey, leaving the solar system behind, never to return. Its brief visit had already provided a wealth of data, and its close pass near Mars had made it the subject of some of the most detailed observations of an interstellar comet in history. But the story of 3IATLAS was far from over. As the data continued to flow in, scientists would begin to piece together the comet's origins, its journey through interstellar space, and what it could reveal about the broader nature of planetary systems and cometary formation. Chapter 7: The Long Road Ahead, Post-Encounter Analysis and Future Discoveries. As 3IATLAS sails past Mars, its grand journey through the inner solar system is nearing its end. The comet, which has captivated scientists and the public alike, has already provided more data than anyone could have imagined. From its green glow to its unexpected chemical composition, 3IATLAS has defied expectations and left the astronomical community with more questions than answers. But the real work is just beginning. With the comet now moving beyond Mars and continuing its path toward perihelion and eventual departure from the solar system, the focus has shifted to post-encounter analysis. This phase will not only help piece together the data captured during its brief passage, but will also shape the way we approach the study of future interstellar objects. The data gathered from 3IATLAS is a treasure trove of knowledge that will continue to yield new insights for years to come. But how exactly will this encounter change our understanding of the universe? And what's next for humanity's exploration of interstellar objects? The post-encounter puzzle, analyzing data from Mars, orbiters, and Earth observatories. As 3IATLAS moves further away from the inner solar system, the Mars orbiters MAVEN, TGO, MRO, and HOPE continue to send back crucial data, which scientists are now processing and analyzing in great detail. The comet's brightening and unpredictable outbursts have already provided a wealth of information, but there is much more to uncover. Each orbiter has contributed unique observations. HiRISE captured high-resolution images of the comet's coma and jets, revealing structural details of the comet's active regions. MAVEN's ultraviolet spectrometer analyzed the emissions from the gases surrounding the comet, allowing scientists to track the chemical composition and determine the nature of the molecules being released. TGO's infrared spectrometers provided data on the temperature variations across the comet's nucleus, helping to reveal which parts were most active and whether the comet's activity was triggered by solar heating. Finally, HOPE probe's broad-field imaging provided context, capturing the comet's position relative to Mars and giving a global view of its trajectory. The data collected from these Mars orbiters is invaluable, but it's only part of the picture. Earth-based observatories such as the Keck Observatory in Hawaii, the Gemini Observatory, and the Hubble Space Telescope have also been tracking 3IATLAS, contributing to the broader dataset. These observatories have provided critical measurements of the comet's brightness, position, and spectral features, and their observations will be crucial in confirming findings from Mars orbiters. Scientists are now working to synthesize the data from both Mars and Earth, building a comprehensive 3D model of the comet's behavior, structure, and composition. The excitement is palpable. Each new dataset brings us closer to understanding the comet's alien chemistry and how it differs from typical solar system comets. But there's still much to analyze. What triggered the comet's unpredictable outbursts? What role did its alien chemical composition play in its behavior? And how did its long journey through interstellar space influence its physical properties? Unraveling the alien chemistry. What we've learned so far. One of the most striking features of 3IATLAS is its alien chemistry. From the moment it was first detected, scientists knew this comet was something special. The green glow, a signature of diatomic carbon, C2, was the first clue, but as spectroscopic data rolled in, astronomers discovered a more complex chemical signature. Unlike typical comets in our solar system, 3IATLAS was releasing an unusual combination of molecules. Carbon dioxide was found in unusually high concentrations, alongside traces of cyanogen, a toxic compound not usually associated with comets. These chemicals raise several questions. Was this the result of solar radiation? Or could 3IATLAS have formed under completely different conditions from the comets we're familiar with? The presence of nickel vapor was especially perplexing. Metals like nickel are rarely released into a comet's coma, especially at this distance from the Sunday. The mystery deepened when scientists discovered that carbon chains, which are typically abundant in comets, were notably depleted in 3IATLAS. Could this depletion be a result of interstellar radiation? Or perhaps it was caused by a long journey through the void, where the comet was bombarded by cosmic rays, breaking down the fragile carbon molecules. As the data continues to come in, researchers are piecing together the puzzle. The alien chemistry of 3IATLAS challenges our understanding of how comets form and evolve. It suggests that comets from other star systems may behave differently than those from the solar system, releasing unique gases and chemicals that have never been seen before. These findings could change how we think about the interstellar medium and the conditions under which comets and other objects form in the galaxy. The legacy of 3IATLAS, how it will change our understanding of the universe. As scientists continue to analyze the data from 3IATLAS, it's becoming clear that this comet has the potential to transform our understanding of the universe. Its unexpected behavior, alien chemistry, and interstellar origins have already challenged the assumptions we had about comets. But there's even more at stake. 3IATLAS is giving us a rare window into the conditions of a star system far beyond our own. The encounter with 3IATLAS is teaching us how comets from other star systems might behave when they pass through the solar system. The data gathered from this encounter will shape future missions to study interstellar objects such as the Comet Interceptor mission, which is scheduled to launch in the coming years. This mission aims to rendezvous with another interstellar object, and the lessons learned from 3IATLAS will be critical in designing observation strategies and spacecraft for future interstellar encounters. Beyond cometary science, the findings from 3IATLAS could also have broader implications for planetary science and astrobiology. The presence of organic molecules and cyanogen in 3IATLAS raises the question: could this comet have delivered prebiotic compounds to its home star system? Could comets like 3IATLAS be the carriers of life's building blocks, spreading the essential elements for life across the galaxy? This idea is still speculative, but the more we learn about cometary chemistry, the more we understand how organic material could travel from star system to star system, providing a potential pathway for life to take root in distant worlds. The encounter with 3IATLAS has also highlighted the value of international collaboration in space exploration. The combined efforts of NASA, the European Space Agency, ESA, and the UAE Space Agency, as well as amateur astronomers and scientists from around the world, have created a global effort to understand this unique object. The teamwork involved in gathering data from Earth-based telescopes and Mars orbiters underscores the importance of global cooperation in the exploration of the cosmos. As more interstellar objects are discovered, it will be essential for scientists to work together across borders and disciplines to share knowledge and uncover the mysteries of the galaxy. What's next? Future interstellar discoveries. The journey of 3IATLAS may be coming to an end, but its impact on our understanding of the universe will continue to resonate for years to come. The data collected during its brief passage through the solar system is just the beginning. As scientists analyze the results, new questions will arise, and future discoveries will build upon the foundation laid by 3IATLAS. While 3IATLAS moves beyond the solar system, new interstellar objects will eventually appear, and the lessons learned from this comet will guide future missions and observations. The upcoming Comet Interceptor mission, launched to study the next interstellar object that enters our solar system, will use the data from 3IATLAS to develop strategies for capturing and analyzing similar visitors. The legacy of 3IATLAS is also a reminder of how much we still have to learn. The galaxy is full of mysteries, comets, asteroids, and planets that have traveled across light years of space. Some of these objects may hold the keys to understanding the formation of stars and planetary systems, while others could provide clues to the origins of life. 3IATLAS's alien chemistry and its unpredictable behavior highlight just how much more there is to discover about the cosmos. In the end, 3IATLAS will be remembered as more than just a comet. It was a messenger from another star system, a cosmic traveler that brought with it the secrets of distant worlds. Its visit challenged our assumptions, expanded our knowledge, and opened new doors for future exploration. As we continue to study its data, the true significance of 3IATLAS will become clearer, and as the comet continues on its journey, leaving the solar system and fading into the void, it leaves behind a legacy of discovery, one that will inspire future generations to look up and wonder what lies beyond the stars. Chapter 8: 3IATLAS leaves our solar system. As the comet 3IATLAS speeds away from the Sun, its brief but extraordinary journey through the inner solar system draws to a close. The excitement that has surrounded its arrival, its unpredictable flares, mysterious chemistry, and unprecedented behavior has now given way to reflection. 3IATLAS has passed Mars, providing invaluable data that will shape cometary research for decades. But its time in the solar system is coming to an end. Soon, it will vanish into the vastness of interstellar space, never to return. For the scientists and astronomers who tracked its every move, 3IATLAS has become more than just a comet. It has been a cosmic event, a fleeting encounter with something truly alien. It has challenged our understanding of the cosmos, revealing new insights into how comets form, how they behave, and what they can tell us about the interstellar medium. But now, as 3IATLAS exits our solar system, the data collected from its journey will provide answers to some of the greatest questions about the formation of planetary systems and the possibility of life beyond our solar system. Mars orbiters and Earth-based telescopes. As 3IATLAS began its final approach to the outer reaches of the solar system, Mars orbiters and Earth-based telescopes continued to capture its last moments of activity. The orbiters, including MAVEN, TGO, MRO, and HOPE, had provided unparalleled observations of the comet as it neared perihelion and passed Mars. But now, as the comet continued its journey, the orbiters had one final task: to capture the last spectrum of the comet as it began to fade from view. With its tail gradually dissipating and its coma shrinking, 3IATLAS became more difficult to observe. The data collected from Mars orbiters and Earth telescopes during the comet's final approach would be crucial in providing a complete picture of the comet's behavior. The final measurements taken by MAVEN's ultraviolet spectrometer and TGO's infrared instruments would reveal how the comet's chemical composition changed as it receded from the sunday. These final observations were important not only for understanding the comet's life cycle, but also for confirming the data collected earlier in its journey. For HiRISE on MRO, the task was to capture one last high-resolution image of 3IATLAS before it passed beyond the orbit of Mars. With the comet's activity starting to wane, this final image would be critical in studying the comet's coma structure, its jets, dust, and gaseous emissions, providing the final data needed to understand how it had evolved during its close pass through the solar system. Meanwhile, Earth-based telescopes like Keck Observatory and Gemini Observatory were continuing to track 3IATLAS's position in the sky, even as it faded from view. These observations provided an additional layer of data that, when combined with Mars-based measurements, would offer a comprehensive understanding of the comet's journey through the solar system. It was an international effort. Scientists from around the world had worked together to capture every moment of this rare and extraordinary event. A new era of interstellar exploration. As 3IATLAS moves beyond the reach of our solar system, it will continue on its hyperbolic trajectory, heading back into the vast void between stars. Its time in the sun's gravitational influence is over, and it will never return. But the comet's legacy will endure. The data gathered during its journey has opened a new chapter in the study of interstellar objects. In fact, 3IATLAS has set the stage for future research that will change the way we look at the galaxy. The encounter with 3IATLAS has revealed more than just the chemical composition of a single comet. It has illuminated interstellar space, showing us how objects from other star systems behave as they travel through our solar system. As 3IATLAS passed through the inner solar system, it provided a unique opportunity to study the interstellar medium, the space between stars. The chemical changes observed in 3IATLAS due to radiation, cosmic rays, and solar heating have given scientists a better understanding of how objects from other star systems can carry alien chemistry into our own. This encounter has also sparked new questions about the role of comets in the galaxy. Could interstellar comets be the vehicles for delivering organic molecules, the building blocks of life, to distant planets? Could comets like 3IATLAS hold the seeds of life, spreading chemical compounds across the galaxy? These are questions that will drive future research and exploration, as the study of interstellar objects becomes an increasingly important field of planetary science. The data from 3IATLAS will also shape future missions designed to study other interstellar objects. The upcoming Comet Interceptor mission, set to launch in 2029, will be tasked with studying an interstellar object that will pass through our solar system in the coming years. The lessons learned from 3IATLAS will inform how we prepare for and capture future interstellar visitors. This mission, along with others that will follow, will continue the work that 3IATLAS began, studying the alien nature of interstellar objects and what they can teach us about the formation of planetary systems, galaxies, and even the potential for life beyond Earth. The end of the beginning. What's next for 3IATLAS? As 3IATLAS moves farther from the solar system, its data will continue to be analyzed and interpreted. The final observations will help close the book on this remarkable cosmic encounter, but they will also open new doors for understanding the true nature of interstellar comets. The comet's chemical anomalies, its unpredictable behavior, and its alien glow have already changed how scientists think about comets and interstellar objects, and this research will shape future missions for years to come. Although 3IATLAS will never return, the impact of its visit will continue to resonate. The science and knowledge gained from this encounter will provide new insights into the chemistry of the galaxy, the interstellar medium, and the processes that shape the evolution of star systems. We have only begun to scratch the surface of what 3IATLAS can teach us, and the results of its study will continue to be analyzed for years to come. As the comet fades into the darkness of space, it will become just another distant memory, a cosmic traveler that once passed through our solar system, leaving behind a trail of mystery and discovery. But in the world of space science, no object is ever truly forgotten. 3IATLAS's legacy will live on in the data collected, the theories proposed, and the new missions inspired by its passage through our cosmic neighborhood. The long road ahead for 3IATLAS may be a lonely one, but for those who witnessed its journey, the comet's legacy is just beginning. The questions it raised, the discoveries it sparked, and the insights it provided will continue to shape our understanding of the universe long after it disappears from view. The end of one journey, the beginning of another. 3IATLAS's departure from the solar system marks the end of an extraordinary encounter. Its time in our cosmic neighborhood was brief, but its impact will echo through the annals of space exploration for years to come. As it moves into the vast, dark expanse of interstellar space, the comet leaves behind a legacy of discovery, insight, a legacy that will continue to inspire future generations of astronomers, planetary scientists, and explorers. For now, 3IATLAS fades into the cosmos, just another distant object drifting through the stars. But its story is far from over. The data it has provided will fuel the curiosity of scientists for decades to come, pushing the boundaries of what we know about the universe. And as we look to the future, we can only wonder, what other alien travelers will come our way? What new discoveries will they bring? For now, we say goodbye to 3IATLAS, but the journey of discovery it started will continue to unfold. The universe, vast and full of mysteries, is waiting for us to explore. And thanks to 3IATLAS, we are one step closer to understanding the mysteries of the stars, the legacy of 3IATLAS, and the future of interstellar exploration. As 3IATLAS drifts farther into the vastness of space, we are left with a treasure trove of data, observations, and lessons that will shape the course of interstellar exploration for years to come. The comet's brief but spectacular journey through the inner solar system has provided insight into the chemistry of distant stars, the behavior of interstellar objects, and the mysteries of planetary formation knowledge that will continue to influence the way we explore the galaxy. For centuries, comets have been considered the messengers of the solar system, carrying the remnants of our planet's formation and offering clues about the early history of the Sun and its planets. But 3I-ATLAS was something entirely different. It came from beyond our solar system, from a distant star system that we have no direct knowledge of. Its unexpected arrival and behavior shattered our understanding of comets, forcing us to reconsider what we thought we knew about these cosmic wanderers. What 3I-ATLAS has revealed is nothing short of extraordinary. Its alien chemistry, with molecules like cyanogen and nickel vapor, pushed the boundaries of what was believed possible for a comet. Its unpredictable outbursts, sudden brightening, and volatile behavior have shown us that comets from other star systems are not just cold, icy rocks. They can be complex, dynamic, and even explosive. And as we analyze the data from this interstellar visitor, it becomes clear that the universe is far more diverse and mysterious than we ever imagined. The legacy of 3I-ATLAS is not just in the data it has provided, it's in the questions it has raised, the new avenues of research it has opened, and the discoveries that are yet to come. This comet has shown us that the interstellar medium, the space between the stars, is not an empty void, but a rich, complex environment that can shape the very chemistry of objects that pass through it. 3I-ATLAS has taught us that the galaxy is alive with movement, with comets, asteroids, and other objects traveling across vast distances, bringing with them the remnants of distant worlds and systems. As 3I-ATLAS leaves our solar system, it is not the end of its story, it is the beginning of a new chapter in interstellar exploration. The lessons learned from its chemistry, structure, and behavior will guide future missions to study other interstellar objects. The Comet Interceptor mission, set to launch in 2029, will visit the next interstellar object that enters our solar system. The data from 3I-ATLAS will provide the groundwork for the design and implementation of this mission, helping scientists understand what to expect when they encounter the next alien traveler. The future of interstellar exploration is just beginning. The success of the 3I-ATLAS mission, an international effort involving NASA, ESA, UAE Space Agency, and countless astronomers, has demonstrated the power of global collaboration in space science. As the Comet Interceptor and future missions seek to explore objects from other star systems, we are reminded that the galaxy is vast, full of unknowns, and that the more we learn, the more questions arise. But beyond the science, there is something truly humbling about the discovery of interstellar objects like 3I-ATLAS. They remind us that our solar system is not isolated, it is part of a much larger and more intricate web of stars, systems, and galaxies. Comets like 3I-ATLAS are not just visitors to our cosmic neighborhood, they are travelers from distant star systems, each carrying secrets of the universe's past, offering us a glimpse of worlds far beyond our own. They challenge our ideas, expand our understanding, and ignite our curiosity about the vastness of space. Looking forward, 3I-ATLAS will continue to inspire and inform the way we approach the study of interstellar objects, planetary systems, and the broader cosmos. Its legacy will live on in the research and missions that follow, serving as a reminder that we have only begun to scratch the surface of what's out there. The galaxy is alive with activity, with alien worlds, interstellar wanderers, and cosmic mysteries just waiting to be discovered. And perhaps most importantly, 3I-ATLAS has reminded us of our place in the universe. In the grand scheme of the cosmos, we are just one small piece of a vast interconnected whole, but that doesn't make our curiosity any less important. 3I-ATLAS has shown us that every piece of data, every question, and every discovery matters. We are not just observers of the universe, we are active participants in uncovering its secrets. As we look to the future, we do so with a renewed sense of wonder, curiosity, and awe. As 3I-ATLAS fades into the distant cosmos, we say goodbye to this alien visitor, but its legacy will live on in the discoveries that follow. And when the next interstellar comet enters our solar system, we will be ready to greet it, study it, and learn from it, just as we did with 3I-ATLAS. The journey of exploration is never truly over, it's just beginning.